Jai Hind everyone. I am Shruti Jain, Assistant Professor, MCA Department, Ajay Kumar Garg Engineering College, Ghaziabad. The topic that I am going to discuss today is concurrency control technique. This topic has been covered under the database management system subject. The code is BMC 204 and the students the target students are MCA first year, second semester students. So, concurrency control basically talks about when we have multiple transactions being executed at a certain point of time, the concurrent execution of the transaction. So, concurrency control is a management of concurrent transaction execution. The DBMS implements these concurrency control techniques to ensure that we get a serializable schedule. One after the other transactions get executed and isolation of the transactions in order to guard the consistency and the integrity of the database. It can be performed by DBMS with various methods like we have the locking method, the time stamping method and the optimistic methods. So, let's start with the first protocol, that is the lock based protocol. The lock based protocol says that we have two types of locks over here. The first lock is the lock exclusive and the lock shared. The exclusive lock says that the data item can be both read as well as be written, and when we are talking about the shared mode, here the data item can only be read and the shared lock can be requested using the lock as instructions. Now, the lock based protocol basically says that whenever we apply a lock onto a transaction, the other transaction cannot acquire that lock until and unless that the transaction that has already taken a lock will unlock the transaction. Only then that variable can be locked by some other transaction. So, a lock on the data item specifies the status of the item with respect to the possible operations like read and write that can be applied to it. So, if a transaction T wants to modify a data item, a lock must be associated with that item. If any other transaction, say T2, already access the same data item, T1 has to wait until T2 gives up the lock. Otherwise, T1 locks the data item. So, we have the lock compatibility matrix. The lock compatibility matrix says if we are applying a shared lock, this shared lock can be accessed by other transactions also. That means multiple transactions can read a data in the shared lock, but if a shared lock has been applied and some other transaction wants to apply the exclusive lock, that is not possible because the exclusive mode talks about the reading and writing of the database. So, a transaction may be granted a lock on an item if the requested lock is compatible with the locks already held on the item by any other transaction. So, if we see over here, whenever the exclusive lock has been applied, then no other transaction can even go for the shared lock. The shared lock can be taken up by multiple transactions, but exclusive lock should be taken up by a single transaction at a particular point of time only. Any number of transactions can hold shared locks on an item, but if any transaction holds an exclusive lock on the item, no other transaction may hold any lock on that item. If a lock cannot be granted, the requesting transaction is made to wait till all the incompatible locks held by other transactions have been released. The lock is then granted. So, for example, we have a transaction 2 which has taken a shared lock on A. So, it will apply for the shared lock first. It will tell what it really wants to do. Shared lock only talks about the reading of the data. So, it reads that variable A, unlock. Unlock means that now it has released that shared lock. It will again acquire a shared lock on B. It will read that data, unlock the lock that it has acquired, that is a shared lock, and then it will display A plus B. If any of the data item has been locked, it needs to be unlocked so that other transactions may access that lock later on. So, locking as above is not sufficient to guarantee the serializability. That is, if A and B get updated in between the read of A and B, the displayed sum would be wrong. So a locking protocol, it is a set of rules that are followed by all the instructions or by all the transactions while requesting or releasing the lock. So this is the pitfalls or the shortcomings of the lock-based protocol. Suppose we have acquired an exclusive lock on B. Now when this lock exclusive has been acquired, the updations can be made, the read and write updations has been made, but this lock has not been released here. Now, by that time, the transaction T4 came up, which took a shared lock on A, it read, and now it is trying to have a lock on B, the shared lock on B. But this has to wait because until and unless it will release the lock, this transaction cannot take the lock. Here, the lock has not been released, so it will keep on waiting. After that, then again came the transaction T3. Now it wants the exclusive lock on A, whereas this A has already taken a shared lock on A, but it has not unlocked it. So this transaction here also will wait. So when transaction T4 is waiting for T3 to release the lock and T3 is waiting for T4 to release the lock, this enters into a deadlock condition because no one is ready to release the lock for the sake of other and both the transactions are waiting indefinitely. So in that case, neither T3 nor T4 can make a progress. Such a situation is known as a deadlock situation. So to handle a deadlock, either T3 or T4 must be rolled back and the locks can be released. So we have the two-phase locking protocol. Here we have seen that there is a situation of a deadlock where the starvation can take place because both of them are indefinitely waiting for the resources or for the transactions to release the lock. So to avoid that starvation of the transactions, we use the two-phase locking protocol. We have two phases. The first phase is a growing phase where the transactions are only obtaining the locks and no transaction is releasing the lock. When we are talking about the shrinking phase, the transactions are releasing the locks but they are not obtaining any of the lock. Though this phase also, this locking protocol does not ensure freedom from deadlocks, but still we can avoid the starvation problem up to a certain extent. So let's take an example over here. We have the lock S, the shared lock taken for a variable A by the transaction T1. Because this is a shared lock, the shared lock can also be taken up by the transaction 2. Now, it has taken, the transaction T1 has taken another lock on, exclusive lock on variable B. So, when it is acquiring the locks from here to here, this phase is known as the growing phase. That is the phase 1. For the transaction 2, it started taking the locks and the growing phase is still here because it is acquiring the lock X on D as well. As soon as this unlock state starts, this state is the shrinking phase for T1. When it is in the shrinking phase, it cannot acquire any lock. Once it is taking the unlock, it is unlocking, it will remain into the unlocking state only, the shrinking phase only. The shrinking phase for transaction T2 starts from here where it is releasing the locks. So this is the two-phase protocol. How is it implemented? We have a concept of the lock manager which can be implemented as a separate process to which the transaction sends a lock and unlock the request. The lock manager replies to the lock request by sending a lock grant message or a message asking the transaction to roll back if there is a deadlock. The requesting transaction waits until its request is answered. The lock manager maintains a data structure called the lock table to record the granted locks and the pending locks. So this lock table is usually implemented as an in-memory hash table indexed on the name of the data item that is being locked. So if we look at this table, this is the lock table that is there. So the black rectangles here indicate the granted locks, white ones indicate the waiting requests. The lock table also records the type of the locks that are granted or requested. New request is added to the end of the queue of the request for the data item, and it is granted if it is compatible with all the earlier locks. Like we have seen that the shared lock can be shared by multiple transactions. Unlock requests result in the request being deleted, and the later requests are checked to see if they can be granted now. If the transaction aborts, all the waiting or the granted requests of the transactions are deleted. The lock manager may keep a list of the locks that are held by each transaction to implement this efficiently. The next protocol that we have is the graph-based protocol, which is an alternative to the two-phase locking. Here we are having the partially ordered sets wherein the edge from DI to DJ, then any transaction that is accessing both DI and DJ must access DI before accessing DJ. That means if we have it from here to here, this needs to be accessed first, only then this node will be accessed. So the tree protocol, it is a simple kind of a tree graph protocol where the exclusive locks are allowed. We do not allow the shared locks because when we are talking about the graph-based protocol, it says that the first node should be accessed, only then the other node will be accessed. The first lock by any of the transaction may be on any data item. There is no restriction on any of the data item when we are applying the lock for the first time. Subsequently, a data queue can be locked by TI only if the parent of the queue is currently locked by TI. That means at the first stage, I can lock any of these nodes. But if suppose I locked these, I applied a lock on this. Now, I can only lock this node only when the parent node is having a lock onto it. In case the parent node is not locked, I cannot put a lock onto the child node. But the data items can be locked at any time. A data item that has been locked and unlocked by TI cannot subsequently be relocked again. That means only once we can unlock or lock a data item, it cannot be relocked. So the tree protocol ensures the conflict serializability as well as the freedom from the deadlock. Unlocking may occur earlier in the tree locking protocol than in the two-phase protocol. Shorter waiting times and an increase in concurrency. Protocol is deadlock free. There is no rollback required because we keep a check whether the parent node is locked or not. But the drawback, the protocol does not guarantee the recoverability or the cascade freedom. Need to introduce the commit dependencies to ensure whether the recoverability can be done or not. The next, transactions may have to lock the data item that they do not access. Increase locking overhead and additional waiting time because every time the locking is to be done, this leads to a potential decrease in the concurrency. So let's take an example. We have, we'll first try to check whether we can put any of the transactions or not. So we have T1, T2, T3 wherein the locks have been acquired and this is already given, the schedule. This is a tree structure. Now we'll see whether we can have a serializable schedule from here or not. So first of all, it has applied a lock on B, exclusive lock on B. So exclusive lock on B has been applied over here. Then another transaction T2 came and it has applied a exclusive lock on D because in the first time we can apply a lock at any place. It needs to apply the lock exclusive on D. That is possible because the parent node is already locked. So this is locked. It also wanted to apply a lock on H. This can also be done because the parent node is already locked. Now it wants to unlock XD. This can be done because the node can be unlocked at any point of time. This is unlocked. Now the transaction T1 again wants to put a lock on E. This is possible because the parent node is locked. On D, again the lock can be put. by some other transaction. So that is possible. This transaction cannot put a lock again. B can be unlocked because the lock can be unlocked at any time, and E is unlocked because there is no hierarchy in that case. H can be unlocked here. B is again taken a lock by some other transaction, and then E can be locked because the parent node has been locked, and then all this. So this is how a tree structure can check whether the locks can be applied or not. With this, now let's try to make a graph. The graph says when we have applied a lock over here and we are making a changes onto some other place. So we have lock X, exclusive lock being taken up by B, but B is again a lock has been acquired here. That means once this B has been unlocked, it has been taken up here. There is a serializability between T1 and T3. So we have a graph node going from T1 to T3 because B is being accessed by T1 first and by T3 next. Next, coming to D, this lock X has been applied on D, and this when unlocked has been taken up by the T1 transaction. So there is again a serializability going from T2 to T1. So we have another node going from T2 to T1 in this direction. Next, coming to H, this H is not being used at any place. We have unlocked. Then lock X at E. E is being used again over here only when it is being unlocked by transaction T1. So this lock E going from T1 to T3, we already have an H from T1 to T3. Lock X at D, this D is not being taken care of later on. These are unlocked. Now the lock has been applied on B but is not taken up later on. Lock has been applied on E but not taken up at the end. Lock at G is not taken up. So we have a schedule like this. So the serializable schedule that we get from here is T2 to T1 to T3. Since there is no cycle formed here, we can say that this is a serializable schedule. Timestamp protocol. The timestamp protocol talks about the write timestamp and the read timestamp, where the write timestamp is the latest timestamp of any transaction that is being executed, that has executed the write successfully. The read timestamp is the latest timestamp of any of the transaction that has executed the read queue successfully. The timestamp talks about, says that the transaction that has come at first will be executed first. Only then the new transaction that is coming into the system will be taken up. So there are two simple methods for implementing this scheme. We use the value of system clock as a timestamp, that is the transaction timestamp is equal to the value of the clock when the transaction enters into the system. We use a logical counter that is incremented after a new timestamp has been assigned, that is the transaction timestamp is equal to the value of the counter when the transaction enters into the system. Each transaction is issued a timestamp when it enters the system. If an old transaction has a timestamp Ti, the new transaction will have the timestamp such that the timestamp of the previous transaction is less than the timestamp of the new transaction. So let's understand it with the help of an example. We have different rules written over here and we have three transactions. The timestamp of T1 is 100, the timestamp of T2 is 200 and the timestamp of T3 is 300. The T1 is first reading the variable A. So when the transaction is reading a variable A, it checks whether the write timestamp of A is greater than the timestamp of Ti. So the write timestamp of A is 0 over here. Is it greater than 100? No, it is not greater than 100. So in that case, what will do? It will execute the read operation and will keep the read timestamp of A as maximum of read timestamp of A, that is 0 initially, and the timestamp of Ti is 100. So this read timestamp of A becomes 100. Next came the transaction T2 with read, Again, it checks the write time stamp of B is greater than 200, that is 0 greater than 200. No. In that case, the read time stamp of B becomes the 200 here. Then comes the write C. We'll check with this rule. The write says if the read time stamp of C, the read time stamp of C is 0 here. Is it greater than the timestamp of Ti, that is 100? 0 is greater than 100. That is false. So what it will do, it will again check the second one. Write time stamp of C, the write time stamp of C is 0. Is it greater than 100? That is again false. So what we'll do, the write time stamp of C will be the timestamp of Ti. The Ti is 100. So the write time stamp of C becomes 100. Next comes read B for transaction T3. The write stamp of B, that is 200, is 200. Sorry, write time stamp of B is 0. 0 greater than 300, that is false. So in that case, it will set this to 300. Again for read C, it will again check and it will read that timestamp of C as 100 here. Now comes this write B. This write B, when this comes, it says if the read timestamp of B is greater than the timestamp of Ti. Read timestamp of B is 300. It is greater than the timestamp of 200. This transaction will roll back. Reason being, when we do not allow the read operation of a new transaction before the write transaction in the previous transaction. Write into the data item of the previous transaction. This leads to the inconsistent database and hence this transaction T2 has to roll back. This is how the timestamp protocol works. Deadlock. How do we handle that deadlock? We have various deadlock prevention schemes where we require that each transaction locks all its data item before it begins the execution. It also imposes a partial ordering of all data items and require that a transaction can lock data item only in the order specified by the partial order. There are necessary conditions for the deadlock. The mutual exclusion, where each resource can be held by only one transaction at a time and other transactions must wait for it to release. The other one is hold and wait. Transaction can request the resources while holding on the resources already allocated to them. No preemption. Resources cannot be taken away from a transaction forcibly and the transaction must release them voluntarily. Circular wait. Transactions are waiting for the resources in the circular chain where each transaction is waiting for the resource held by a next transaction in the chain. This leads to the deadlock, that is indefinite blocking, because if there is a circular wait, the transactions are blocked indefinitely. There is a problem of starvation and no transaction will execute. There is a problem of system stagnation because it leads to the stagnancy in the system where no transaction is executing. Inconsistent data because some of the transactions might have executed, some might not have. And it is very difficult to detect the deadlock and to resolve them. So in that case, we need to roll back all those transactions. So we have certain deadlock prevention strategies, wait die scheme, where it says that suppose we have T1 and T2 transactions, where T1 is an older transaction and T2 is a newer transaction. The older transaction will wait for the younger transaction to release a data item, but the younger transaction will not wait, will never wait for the older one. They are rolled back instead. So older transaction keeps on waiting and the new transaction, if they do not get any of the data item that they are waiting for, it will roll back. So a transaction may die several times before acquiring the needed data item. But wound wait says that older transaction will force the rollback of the younger transaction instead of waiting for it. If suppose T1 is in wait of a lock and that lock has been acquired by T2, it will forcibly roll back this T2 because it will not wait for T2 to release the resource and then the transaction T1 will work. So here we have fewer rollbacks as compared to the wait die scheme. The next scheme that we have is the timeout based scheme, wherein a transaction waits for a lock only for a specified amount of time. After that, that wait time out and the transaction is rolled back. Here the deadlock is not possible. It is simple to implement, but the problem occurs is it is very difficult to identify what is the the value that needs to be kept for the timeout interval. So that is all for today. Thank you.